So we already have Spider-Man riding on top of a police car, and he's 82 kilograms, and the car is moving at 20 meters per second. So all of a sudden, in comes the Green Goblin. All right, now the Green Goblin, of course, has his pumpkin bombs, and what he does is he's going to take one of his pumpkin bombs and he's going to throw it at Spider-Man. So in order to not get hit by the pumpkin bomb, I'm going to draw some throwing lines. There we go. So in order to not get hit by the pumpkin bomb, Spider-Man is going to jump straight up. Now he's already moving forward, but then he's also going to jump straight up. And when he jumps up, so he's going to jump up in order for the bomb to go underneath him. He's going to jump up and he's going to use 4,500 newtons for 0.13 seconds in order for him to miss the pumpkin bomb. All right, so what we're going to do is we're going to find out when he's jumping, what is his velocity after he jumps. And we're going to use momentum in order to do this because we're practicing with momentum, so that's what we're going to do. So we are going to sort of piece things together and see what we can figure out. Now, first of all, he's just going along in the car. He's got momentum to start with. Okay, so he's got momentum from the car because he's just going forward. And the momentum that he started with would just be mv. Now, his mass is 82. He's just riding on the car, which has a v of 20. So we have his mass already. We know we've got a v of 20. So we can use the 82 and the 20 to find out how much momentum he started with. So P equals mv, we multiply the two together, and we're looking around 1,640 kilogram meters per second of momentum to start with before he even does anything with pumpkin bomb. Then when the pumpkin bomb kicks in, he is going to jump up in order to miss it. So he is going to jump straight up using a force for time. Well, force and time gives us his impulse. So his impulse or his vertical momentum will be force times time. So if we do the 4,500 and we multiply that by the 0.13, we get about 585 kilogram meters per second of momentum going up. Now, if we take these two and we put them together, it looks something like this. That's what he would do. I mean, if he was riding on a car going forward and he jumps up, he's not just going to go forward, he's not just going to go up, it'll be the combination of the two, and he will go off at an angle something like this. So we can use his momentum that he started with, plus the impulse and momentum he gained by jumping up, to figure out what this overall momentum must be diagonally. And this is just a right triangle, so it's got to use some Pythagoras and some trig and stuff like that to figure out the angle and figure out the length of the hypotenuse. Momentum is a vector quantity, so it can go together just like velocity and displacement vectors. So if we use Pythagoras, we got the 1640 here, we've got 585 over there. We can find out that his momentum this way is about 1,740, and we can use our trig, probably tan theta, using these two to find the angle here, and that will be about 20 degrees. So now I know his momentum after he jumps. The momentum from the car plus his jumping momentum put together got something like this. So to find out his velocity afterwards, well, velocity is just going to be his momentum divided by his mass, and momentum is going to be the 1740. I have his mass from before, so I just have to use the 1740, divide that by his mass of 82, and I can find out how fast he's going. And then dividing by those two, we get about 21.2 meters per second. And the angle would be the same as the momentum angle. That's the way he's going, so it'd be 21.2 at about 20 degrees. And that would be his velocity after jumping to avoid the pumpkin bomb. Now again, you could do this F equals ma VAT, but using momentum is a nice way to do it as well.